ਤੁਸੀਂ ਕਦੇ ਸੰਗੀਤਕਾਰਾਂ ਨੂੰ ਪ੍ਰੋਗਰਾਮ ਸ਼ੁਰੂ ਹੋਣ ਤੋਂ ਪਹਿਲਾਂ ਆਪਣੇ ਸਾਜ਼ ਟਿਊਨ ਕਰਦਿਆਂ ਵੇਖਿਆ ਹੈ? ਕੀ ਤੁਹਾਨੂੰ ਪਤਾ ਹੈ ਕਿ ਇਹ ਕੰਮ ਕਿਵੇਂ ਕੀਤਾ ਜਾਂਦਾ ਹੈ? ਆਓ ਦੱਸੀਏ।
ਪਿਆਰੇ ਵਿਦਿਆਰਥੀਓ, ਬੀਟਸ ਐਂਡ ਡੋਪਲਰ ਇਫੈਕਟਸ ਇਨ ਸਾਊਂਡ ਦੀ ਅੱਜ ਦੀ ਇਸ ਕਲਾਸ ਵਿੱਚ ਤੁਹਾਡਾ ਸਾਰਿਆਂ ਦਾ ਸਵਾਗਤ ਹੈ। ਪਿਛਲੀ ਕਲਾਸ ਵਿੱਚ ਅਸੀਂ ਸਟੈਂਡਿੰਗ ਵੇਵਸ ਬਾਰੇ ਪੜ੍ਹਿਆ ਸੀ। ਅਸੀਂ ਜਾਣਦੇ ਹਾਂ ਕਿ ਜਦੋਂ ਇੱਕੋ ਹੀ ਟਾਈਪ, ਐਂਪਲੀਟਿਊਡ ਅਤੇ ਫ੍ਰੀਕੁਐਂਸੀ ਦੀਆਂ ਦੋ ਪ੍ਰੋਗਰੈਸਿਵ ਵੇਵ ਟ੍ਰੇਨਸ ਇੱਕੋ ਸਪੀਡ ਨਾਲ ਇੱਕ ਸਟ੍ਰੇਟ ਲਾਈਨ ਵਿੱਚ ਆਪੋਜ਼ਿਟ ਡਾਇਰੈਕਸ਼ਨਸ ਵਿੱਚ ਚਲਦੀਆਂ ਹੋਈਆਂ ਸੁਪਰ ਇੰਪੋਜ਼ ਕਰਦੀਆਂ ਹਨ ਤਾਂ ਉਹ ਸਟੇਸ਼ਨਰੀ ਵੇਵਸ ਪ੍ਰੋਡਿਊਸ ਕਰਦੀਆਂ ਹਨ। ਹੁਣ ਦੇਖਣਾ ਇਹ ਹੈ ਕਿ ਜੇ ਦੋਹਾਂ ਦੀਆਂ ਫ੍ਰੀਕੁਐਂਸੀਜ਼ ਵਿੱਚ ਥੋੜਾ ਜਿਹਾ ਫਰਕ ਹੋਵੇ ਤਾਂ ਕੀ ਹੋਵੇਗਾ। ਅੱਜ ਅਸੀਂ ਇਸ ਸਵਾਲ ਦੇ ਜਵਾਬ ਦੇ ਨਾਲ ਹੀ ਸਾਊਂਡ ਵਿੱਚ ਡੋਪਲਰ ਇਫੈਕਟ ਵੀ ਪੜਾਂਗੇ। But before that, let me share the learning objectives for today's lesson with you.
On completion of this topic, learners will be able to describe beats and their formation, define Doppler effect and discuss its validity, explain the Doppler effect for different situations of change in frequency, derive the mathematical expression for the Doppler shift for the specified case.
When we fly in a passenger plane, we may often hear a fluctuating monotonous sound. That is a beat frequency caused by engine vibrations at two close frequencies. When two sound waves of slightly different frequencies traveling in a medium along the same direction, when they superimpose on each other, the intensity of the resultant sound wave at a particular position rises and falls regularly with time. This phenomenon of periodic variation in the intensity of sound when two sound waves of nearly equal frequencies superimpose on each other is called beats. The time interval between two successive beats or two successive maxima of sound is called beat period, whereas the number of beats produced per second is called the beat frequency. However, it is found that the number of beats per second or the beat frequency is equal to the difference in the frequencies of two superimposing component waves. If nu1 and nu2 are the frequencies of the two waves, then the beat frequency B is equal to nu1 minus nu2 provided nu1 is slightly greater than nu2. If the beats formed are more than 10 per second, they go unheard for human ear. In other words, the human ear can detect the beats only if the difference in frequencies of the two harmonic waves is less than 10. It is because of the persistence of hearing. Do you remember that the impression of a sound heard by our ears persists on our mind only for 1/10 of a second? Therefore, if another sound is heard before the passage of 1/10 seconds, the impression of the two sounds mix up and our mind does not distinguish between them. Hence, it is clear that we can hear the beats only if the difference in the frequencies of two superimposing component waves is less than 10. The formation of beats can be studied both graphically and analytically. First of all, let us discuss the formation of beats by graphical method. Let us consider two harmonic wave trains of slightly different frequencies traveling in a medium. However, for the sake of simplicity, we consider the two waves of equal amplitudes, but with frequencies nu1 equal to 40 Hz and nu2 equal to 42 Hz. In t equal to 1/4 second, first wave completes 40/4, that is 10 vibrations. whereas the second wave completes 42 by 4, that is 10.5 vibrations. Thus, compression due to the first would fall on rarefaction due to second. The resultant amplitude would become minimum and hence resultant intensity of sound would be minimum. In t equal to 1 by 2 second, the first wave completes 40 by 2, that is 20 vibrations, whereas the second wave completes 42 by 2, that is 21 vibrations. Thus, compression due to first wave would fall on compression due to the second wave. The resultant amplitude would become maximum and hence the resultant intensity of sound would also be maximum. Thus, one beat is formed in half of a second. Similarly, another beat is formed in the next half second. Hence, number of beats per second is equal to 2, which is equal to the difference in the two frequencies. Let us see some more examples of beats formation.
Let us consider two wave trains of same amplitudes and frequencies 400 and 401 Hz respectively. We get beats of frequency 1, but when the two wave trains are of frequencies 400 and 405 Hz, we get beats of frequency 5. And when the two wave trains are of frequencies 400 and 410 Hz, we get beats of frequency 10.
Let us now discuss the formation of beats by analytical method. Let us consider two harmonic waves of equal amplitudes but of wavelengths lambda 1 and lambda 2 traveling in a medium in the same direction and with the same speed v along the positive x-axis. Let the wave functions of the first wave be y1 equal to r sine of 2 pi by lambda 1 into vt minus x, and of the second wave it be y2 equal to r sine of 2 pi by lambda 2 into vt minus x. y1 can be written as y1 equal to r sine of 2 pi into vt by lambda 1 minus x by lambda 1. We know that the frequency is equal to the ratio of velocity and wavelength. Hence, if nu1 be the frequency of first harmonic wave or v by lambda 1, the expression for displacement becomes y1 equal to r sine of 2 pi into nu1 t minus x by lambda 1. Similarly, the wave function of the second wave be y2 equal to r sine of 2 pi into nu2 t minus x by lambda 2. If the listener is situated at x equal to 0, then the variations in the displacements of the two waves at this point would be y1 equal to r sine 2 pi into nu1 t and y2 equal to r sine 2 pi into nu2 t. According to the principle of superposition of the two wave pulses, the displacement of the resultant wave pulse y would be equal to y1 plus y2. This gives y equal to r into sine 2 pi nu1 t plus sine 2 pi nu2 t. Since sine c plus sine d is equal to 2 sine c plus d by 2 into cos c minus d by 2. Hence, y is equal to 2r sine of 2 pi into nu1 plus nu2 by 2 into t into cos of 2 pi into nu1 minus nu2 by 2 into t. On further solving, we get y equal to 2r sine of pi into nu1 plus nu2 into t into cos of pi into nu1 minus nu2 into t. This equation represents a harmonic wave of frequency nu1 plus nu2 by 2. It is clear that amplitude of the resultant wave A is equal to 2r cos of pi nu1 minus nu2 into t, which varies with time. Amplitude A will be maximum when cos of pi nu1 minus nu2 into t is equal to plus minus 1. In other words, cos of pi nu1 minus nu2 into t must be equal to cos of n pi, where n is equal to 0, 1, 2, 3 and so on. In other words, pi nu1 minus nu2 into t must be equal to n pi. Therefore, t is equal to n by nu1 minus nu2. Hence, the amplitude of resultant wave and therefore resultant intensity of sound will be maximum at times 0, 1 by nu1 minus nu2, 2 by nu1 minus nu2, 3 by nu1 minus nu2 and so on. Since time interval between two successive maxima of sound is equal to 1 by nu1 minus nu2. Therefore, at position x equal to 0, the resultant amplitude as well as the intensity of the sound will be maximum after a fixed interval of time, which is equal to 1 by nu1 minus nu2. Since the frequency is the reciprocal of the time period, the frequency of maximum intensity is equal to nu1 minus nu2. Similarly, the amplitude A will be minimum when cos of pi nu1 minus nu2 into t is equal to 0, or cos of pi nu1 minus nu2 into t must be equal to cos of 2n plus 1 into pi by 2, where n is equal to 0, 1, 2, 3 and so on. Or pi nu1 minus nu2 into t must be equal to 2n plus 1 into pi by 2. Therefore, t is equal to 2n plus 1 by twice of nu1 minus nu2. Hence, the amplitude of resultant wave and therefore resultant intensity of sound will be minimum at times 1 by 2 nu1 minus nu2, 3 by 2 nu1 minus nu2, 5 by 2 nu1 minus nu2 and so on. Here again, time interval between two successive minima of sound is equal to 1 by nu1 minus nu2. Therefore, the frequency of minimum intensity is also equal to nu1 minus nu2. This shows that the frequencies of maximum and minimum intensities of sound on superposition of the two harmonic waves are equal. It is clear that the one maximum in intensity will be followed by a minimum and then by a maximum and so on. Since one beat is formed when the intensity of sound again becomes maximum after once becoming minimum. Therefore, the beat frequency, that is, the number of beats per second, B, is equal to nu1 minus nu2. Do you think we can have some applications of the beats phenomenon in our lives? Musicians make use of this phenomenon of beats in matching the frequencies of their various instruments. The instruments are sounded together, and for one of the instruments, the frequency is gradually altered till the beats disappear. The phenomenon of beats is also used in radio reception in many ways. Another use of beats is to detect the presence of dangerous gases in mines. However, one of the important applications of this phenomenon of beats is to determine the frequency of an unknown tuning fork. If you know the frequency of a tuning fork, say nu1, and B, the beat frequency with nu2 as the frequency of another tuning fork of unknown frequency, then nu2 is simply equal to nu1 plus or minus b. Now, let us see how can we decide the positive or negative sign in this expression for the unknown frequency of a tuning fork. If the prong of the tuning fork is filed a little, its frequency increases, whereas attaching a little wax to one of the prongs, the frequency of the tuning fork decreases. Attaching a little wax to one of the prong is called loading. This fact can be used to decide the positive or negative sign. Let us consider that a little wax is attached to the prong of the tuning fork of unknown frequency. We again find the number of beats produced. If the frequency of the tuning fork is greater than nu1, that means nu2 is equal to nu1 plus b. Then attaching of a little wax would lower its frequency, and the difference in frequencies will decrease, and the number of beats should also decrease. This shows that on attaching a little wax to the prong of the tuning fork of unknown frequency, the beat frequency decreases. On the other hand, if the frequency of second tuning fork is less than nu1 or nu2 is equal to nu1 minus b, then attaching of a little wax would further lower its frequency and the difference in the frequencies will increase. Hence, the number of beats should also increase. Similarly, if the prong of tuning fork is filed, the frequency of the tuning fork increases and the results obtained are found to be opposite to that on loading. That means, if on filing the prong of the tuning fork of unknown frequency, the beat frequency decreases, then nu2 would be equal to nu1 minus b. And if on filing the same prong, the beat frequency increases, then nu2 would be equal to nu1 plus b. It should be clear to you that if the tuning fork of known frequency is loaded instead of tuning fork of unknown frequency, and if the number of beats increases, take positive sign, and if the number of beats decreases, take negative sign. I hope the concept of beats is clear to you. Let us now take our discussion to Doppler effect. ਜਦੋਂ ਵੀ source of sound ਅਤੇ listener ਵਿਚਕਾਰ relative motion ਹੁੰਦਾ ਹੈ, ਤਾਂ listener ਦੁਆਰਾ ਸੁਣੀ ਗਈ sound source ਤੋਂ emitted sound ਨਾਲੋਂ ਵੱਖਰੀ ਹੀ ਸੁਣਾਈ ਦਿੰਦੀ ਹੈ। ਆਮ ਤੌਰ ਤੇ ਕੋਈ ਤੇਜ਼ ਰਫ਼ਤਾਰ ਗੱਡੀ ਹੌਰਨ ਵਜਾਉਂਦੀ ਹੋਈ ਕੋਲੋਂ ਨਿਕਲ ਜਾਵੇ ਤਾਂ ਇਹ ਫਰਕ ਸਾਫ਼ ਸੁਣਿਆ ਜਾ ਸਕਦਾ ਹੈ। Variation in frequency of sound due to the relative motion between a source of sound and the listener is called as the Dopplers effect. The received frequency is higher as compared to the emitted frequency during the approach. It is identical at the instant of passing by, and it is lower during the recession. Let's have a look at some examples.
The frequency of a whistling engine heard by a stationary person remains same when the engine is at rest. The frequency of an engine heard by a stationary person appears to increase when the engine is approaching him, and it appears to decrease when the engine is moving away from him. Similarly, when the engine is stationary and the listener is moving in a car, then the frequency of a whistling engine heard by the listener appears to increase. When the car is approaching the engine, and it appears to decrease when the car is moving away from the engine.
Let us discuss different situations one by one. The first case is when the source of sound is in motion and listener is at rest. Let us consider a source of sound and a listener initially both at rest. If nu be the actual frequency of sound emitted by the source, lambda be the actual wavelength of the emitted sound, and v be the velocity of sound in still air, then lambda would be equal to v by nu. If the source is in motion with velocity vs towards the stationary listener, then the relative velocity of the sound with respect to the source would be v minus vs. So, the source is emitting sound waves of apparent wavelength lambda dash to the listener, which would be equal to v minus vs by nu. If nu dash be the apparent frequency, it would be equal to v by lambda dash, that is v by v minus vs times the original frequency nu. It is clear that nu dash is greater than nu. Therefore, when the source of sound moves towards the stationary listener, the pitch of the sound appears to increase. On the other hand, if the source is moving away from the listener with velocity vs, then apparent frequency of the sound can be obtained by changing the sign of vs, that is, by changing vs by minus vs, and the expression for apparent frequency would be nu dash equal to v by v plus vs into the original frequency nu. It shows that nu dash is smaller than nu. Therefore, pitch of the sound appears to decrease when the source of sound moves away from the stationary listener. Here, it should be noticed that the velocity of the source of sound cannot be greater than the velocity of the sound. Otherwise, the apparent frequency will become negative, which is not possible. Next case is when the source of sound is at rest and listener is in motion. If the listener is in motion with velocity vl towards the stationary source, then the listener will receive some more waves and the extra number of waves would be equal to vl by lambda. Therefore, the apparent frequency of the sound nu dash would be equal to nu plus vl by lambda. On substituting the value of lambda, we get nu dash equal to nu plus vl upon v by nu, or nu dash is equal to nu plus vl by v into nu. It is clear that nu dash is greater than nu. Hence, pitch of the sound appears to increase when the listener moves towards the stationary source of sound. On the other hand, if the listener is moving away from the source of sound with velocity vl, then apparent frequency of the sound can be obtained by changing vl by minus vl, and the expression for apparent frequency would be nu dash equal to v minus vl by v into nu. It shows that nu dash is smaller than nu. Thus, pitch of the sound appears to decrease when the listener moves away from the stationary source of sound. Can you imagine what would be the apparent frequency of sound waves when source of the sound and the listener both are in motion? इस डिस्कशन तो दो सिੱਟੇ ਕੱਢੇ ਜਾ ਸਕਦੇ ਹਨ। ਪਹਿਲਾ, ਜਦੋਂ ਸੋਰਸ ਮੋਸ਼ਨ ਵਿੱਚ ਅਤੇ ਲਿਸਨਰ ਸਟੇਸ਼ਨਰੀ ਹੋਵੇ ਤਾਂ ਡੋਪਲਰ ਇਫੈਕਟ ਵੇਵਸ ਦੀਆਂ ਵੇਵਲੈਂਥਸ ਦੇ ਸਾਈਜ਼ ਵਿੱਚ ਐਪਰੈਂਟ ਚੇਂਜ ਕਾਰਨ ਹੁੰਦਾ ਹੈ। ਦੂਜਾ, ਜਦੋਂ ਸੋਰਸ ਰੈਸਟ ਤੇ ਅਤੇ ਲਿਸਨਰ ਮੋਸ਼ਨ ਵਿੱਚ ਹੋਵੇ ਤਾਂ ਡੋਪਲਰ ਇਫੈਕਟ ਲਿਸਨਰ ਦੇ ਈਅਰਸ ਨੂੰ ਕ੍ਰਾਸ ਕਰਨ ਵਾਲੀਆਂ ਵੇਵਸ ਦੇ ਨੰਬਰ ਵਿੱਚ ਚੇਂਜ ਕਾਰਨ ਹੁੰਦਾ ਹੈ। ਇਹ ਜਾਣਕਾਰੀ ਡਿਫਰੈਂਟ ਕੇਸਿਸ ਵਿੱਚ ਸਾਊਂਡ ਦੀ ਐਪਰੈਂਟ ਫ੍ਰੀਕੁਐਂਸੀ ਡਿਰਾਈਵ ਕਰਨ ਲਈ ਉਦੋਂ ਵਰਤੀ ਜਾਂਦੀ ਹੈ ਜਦੋਂ ਦੋਨੋਂ source ਅਤੇ listener motion ਵਿੱਚ ਹੋਣ। When both the source and the listener move towards each other, first of all, we consider that nu dash is the apparent frequency when the source alone is in motion with a velocity vs towards the stationary listener. If v be the velocity of sound and nu the actual frequency of the sound, then the apparent frequency for the stationary listener nu dash would be equal to v by v minus vs into the original frequency nu. Now, let us consider that the listener is moving with velocity vl towards a stationary source which appears to be emitting waves of frequency nu dash. Due to the motion of the listener, the apparent frequency will further change from nu dash to nu double dash. According to the expressions discussed earlier, nu double dash would be equal to v plus vl by v into nu dash. On substituting the value of nu dash, we get nu double dash equal to v plus vl by v into v by v minus vs into nu. This is equal to v plus vl upon v minus vs into nu. ਇਸ ਐਕਸਪ੍ਰੈਸ਼ਨ ਤੋਂ ਪਤਾ ਲੱਗਦਾ ਹੈ ਕਿ ਜਦੋਂ ਦੋਨੋਂ ਸੋਰਸ ਅਤੇ ਲਿਸਨਰ ਇੱਕ ਦੂਜੇ ਵੱਲ ਮੂਵ ਕਰਦੇ ਹੋਣ ਤਾਂ ਸਾਊਂਡ ਦੀ ਐਪਰੈਂਟ ਫ੍ਰੀਕੁਐਂਸੀ ਇਸ ਦੀ ਐਕਚੁਅਲ ਫ੍ਰੀਕੁਐਂਸੀ ਨਾਲੋਂ ਵੱਧ ਹੁੰਦੀ ਹੈ। ਤੁਸੀਂ ਇਹ ਵੀ ਧਿਆਨ ਦਿੱਤਾ ਹੋਣਾ ਹੈ ਕਿ ਲਿਸਨਰ ਦੀ ਵੈਲੋਸਿਟੀ ਤਾਂ ਸਾਊਂਡ ਦੀ ਵੈਲੋਸਿਟੀ ਨਾਲੋਂ ਜ਼ਿਆਦਾ ਹੋ ਸਕਦੀ ਹੈ, ਪਰ ਸੋਰਸ ਦੀ ਵੈਲੋਸਿਟੀ ਸਾਊਂਡ ਦੀ ਵੈਲੋਸਿਟੀ ਨਾਲੋਂ ਜ਼ਿਆਦਾ ਨਹੀਂ ਹੋ ਸਕਦੀ। ਇਸ ਤਰ੍ਹਾਂ ਨਾਲ ਐਪਰੈਂਟ ਫ੍ਰੀਕੁਐਂਸੀ ਨੈਗੇਟਿਵ ਹੋ ਜਾਵੇਗੀ ਜੋ ਸੰਭਵ ਹੀ ਨਹੀਂ ਹੈ। Similarly, we can obtain the expression for apparent frequency of the sound when both the source and the listener move away from each other. This can be obtained by changing the signs of the velocities Vl and Vs in the expression for apparent frequency. We get nu double dash equal to v minus vl upon v plus vs into nu. There is one more possibility, that is when the source moves towards the listener and the listener moves away from the source. In such a case, apparent frequency due to source moving towards the listener nu dash would be equal to v by v minus vs into the original frequency nu. Due to the motion of the listener away from the source, the apparent frequency would be nu double dash equal to v minus vl by v into nu dash. Hence, the apparent frequency would be nu double dash equal to v minus vl upon v minus vs into nu. In this case, nu double dash may be greater or less than nu depending upon Vl is less than or greater than Vs. However, Doppler effect would be observable only either both Vl and Vs are less than V or both are greater than V. Similarly, the expression for apparent frequency when the source moves away from the listener but the listener moves towards the source can be obtained by changing the signs of both Vl and Vs in the expression nu double dash equal to v minus Vl upon v minus Vs into nu. Hence, the expression for apparent frequency would be nu double dash equal to v plus Vl upon v plus Vs into nu. These are the conditions under the stationary medium. Let us analyze the condition when wind is blowing. We consider that a source of sound is emitting sound waves of frequency nu. Let v be the velocity of sound in still air. Let the wind be blowing with a velocity w. Then the effective velocity of the sound will be V plus W or V minus W, depending upon whether the wind is blowing in the direction of the sound waves or in its opposite direction. I hope the concept of Doppler effect is also now very clear to you. Let me tell you that Doppler effect is used to find out the speed of vehicles by the traffic police. It is also used in radar to detect the location of planes. With this, we come to the end of today's topic. Let us now summarize its contents once. When two sound waves of slightly different frequencies traveling in a medium along the same direction superimpose on each other, the intensity of the resultant sound wave at a particular position rises and falls regularly with time. This phenomenon is called beats. The time interval between two successive beats or two successive maxima of sound is called the beat period, whereas the number of beats produced per second is called the beat frequency. If nu1 and nu2 are the frequencies of the two waves, then the beat frequency B is equal to nu1 minus nu2. What is Doppler's effect? Whenever there is a relative motion between a source of sound and the listener, sound heard by the listener is found to be different from the actual sound. This phenomenon is called the Doppler effect. When source of the sound and the listener both are moving towards each other, then the apparent frequency nu double dash is equal to V plus VL upon V minus Vs into nu. If the listener is at rest and the source is moving towards the listener, then the apparent frequency nu dash is equal to V upon V minus Vs into nu. On the other hand, if the source is at rest and the listener is moving towards the source, then the apparent frequency nu dash is equal to V plus VL upon V into nu. Similarly, when source of the sound and the listener both are moving away from each other, then the apparent frequency nu double dash is equal to V minus VL upon V plus Vs into nu. If the listener is at rest and the source is moving away from the listener, then the apparent frequency nu dash is equal to V upon V plus Vs into nu. On the other hand, if the source is at rest and the listener is moving away from the source, then the apparent frequency nu dash is equal to V minus VL upon V into nu. So now we come to the end of this class. But before that, let us have a quick test to find out how much have you actually absorbed. My first question is, define Doppler's effect. The answer is, according to Doppler's effect, there is a variation in the frequency of sound due to the relative motion between the source of sound and the listener. The next question is, what is the essential condition to obtain beats? The answer is, different sources of sound must have nearly equal frequencies. The beat frequency B is equal to nu1 minus nu2. ਮੈਨੂੰ ਪੂਰਾ ਭਰੋਸਾ ਹੈ ਕਿ ਤੁਹਾਨੂੰ ਬੀਟਸ ਅਤੇ ਡੋਪਲਰ ਇਫੈਕਟ ਚੰਗੀ ਤਰ੍ਹਾਂ ਸਮਝ ਆ ਗਏ ਹੋਣਗੇ। ਪਾਠ ਨੂੰ ਧਿਆਨ ਨਾਲ ਸੁਣਨ ਲਈ ਤੁਹਾਡਾ ਧੰਨਵਾਦ। ਅਗਲੀ ਕਲਾਸ ਵਿੱਚ ਫਿਰ ਮਿਲਾਂਗੇ ਅਤੇ ਕੁਝ ਨਵਾਂ ਪੜਾਂਗੇ।